Hey there, Math 2403. Welcome back to Unit 6, video number 3. Today we're going to do hypothesis tests for the population proportion. Last time we were doing confidence intervals for the population proportion, so many of these things should seem familiar. However, the hypothesis test process is a little more involved. It's a formal process for testing claims about population proportions. So let's get to it. Hypothesis testing is different from confidence intervals in that with confidence intervals, we tend to want to know something about a population parameter. Say we're interested in knowing the mean of a population or a certain proportion number about a population. And we don't really have any other knowledge yet. Hypothesis testing is a little different in that we'll generally be testing a claim about a population value. So someone will claim, I think that 90% of BCIT students will pass a certain course. And now we can test that claim by gathering some data and comparing that against with the value that was claimed. Same with the mean. I could make a claim that the mean score on our midterm will be, under 90%. And then I can gather some data and see if my sample results agree or disagree with this claim. So that's basically what hypothesis testing is all about. There's a claim about a population parameter, we collect some data, and we see if our data is close enough so that it may agree with what was being claimed, or different enough that we would maybe disagree with what's being claimed. The main principle behind hypothesis testing is given here. If, under a given assumption, the probability of a particular observed event is exceptionally small, we can conclude that the assumption is probably not correct. We did sort of this decision making a few times when we were dealing with the t distribution and the z distribution. We made some decisions based on probability, and that's the underlying characteristic that we'll have in this hypothesis test. I thought we'd start out with claims about population proportions. So we'll talk about a parameter pi, and we'll be interested in gathering some sample data to see if our sample result agrees or disagrees with what someone is claiming pi to be. In order to do these tests, it's like confidence intervals. You have to make sure that you're meeting the requirements of the models in order to be able to perform the tests. So when we're talking about proportions, we have to make sure our sample sizes are large enough. And if they're large enough, we know that we end up having our binomial distribution essentially becoming the normal distribution. And then we can use our Z distribution when making probability decisions. And to do that with the proportions, we had that rule for confidence intervals where n times p had to be greater than or equal to 5, or n times q had to be greater than or equal to 1 minus 5. And we have that same rule here for hypothesis testing, except now we will be able to use pi in our formula because someone's going to claim something about the population value. So we'll know, or we will work with a value for pi, even if we don't yet know it for certain. In order to do a hypothesis test, you have to have a test statistic, and they tend to be t-scores or z-scores, or we'll have a few others. We'll learn the chi-square distribution later and the F distribution. But for now, we're familiar with t-scores and z-scores. Basically, they're scores that separate what's likely to happen from things that are not as likely to happen, or they at least help us determine that. So here's a z-score or test statistic for proportions. Knowing this, we can dive into an example. I have provided you with a summary of hypothesis testing. It's a rather long document that goes through all the details, but I thought it would be best to just dive right in and do one. And then and I'll sort of explain what we're doing as we're doing it. So just sort of bear with it on the first example or two, and then maybe read through that document, and hopefully everything will start to make sense as we go through this. We've broken our hypothesis test procedure into an 8-step process. So, I mean, it's rather involved. I'll try to explain why we're doing each step as we're doing it, or I'll just do the step, we'll finish the whole test, and then I'll come back and sort of summarize. So be patient with these. The first one tends to go slow. They won't take as long after you get used to it. So this first one might take a half an hour, but in general, these don't take that long. So here's a little example. We're constructing a large hotel, and we received 1,600 window panes. Of those, 160 were damaged. This is not that unusual because the hotel is being built out in the middle of nowhere, and they can, windows can easily be damaged in delivery. The company delivering them says that on average, we'd expect around 8% of these things to be damaged. So we're going to test their claim. They're claiming that the proportion of broken window panes is 8%. So I'm going to write this in steps. Step number 1 will be the claim. Convert the claim into math. So they are claiming that the proportion of broken windows is equal to 8%. You can see from our data that we're going to say we think it's around 10%. So the question will be, is 10% different enough from 8% for us to say we don't really believe them? Or is 10% close enough to 8% for us to say, yeah, we can't really say they're wrong? So let's get into step 2 and set up some hypotheses. We'll have 2. We have the null hypothesis, which is H subscript 0, and the alternative hypothesis, which is H subscript A. We need to put this claim as one of the 2 hypotheses. These 2 things are opposites of one another. We'll work under the assumption that the claim is correct in this example. We're going to say that our working hypothesis is that 8% of these windows are broken. This is our null hypothesis, or working hypothesis. The claim isn't always the null hypothesis. It is for this one. If the claim includes an equal sign, and by an equal sign I mean any kind of equal sign, less than or equal to, greater than or equal to, or a hard equal to, then the claim is the null hypothesis. But if the claim doesn't have an equal sign in it, then the claim becomes the alternate hypothesis. So setting this up at the beginning is really important. The claim isn't always the null hypothesis. It is only if the claim has some form of equality, as this one does. Then wherever this ends up landing, if it ends up in HO or it ends up in HA, you just write the opposite in the other spot. In this case, the alternate hypothesis is that it's not 8%. It's called the alternate. Let me try that again. Alternate hypothesis. So we figured out what our claim was. When you're doing these later, you'll first have to decide, is this a mu question or is it a pi question, for example? And then you'll have to figure out how it's worded, whether the claim has an equal sign or not. You know, sometimes they could have claimed that pi was greater than or equal to 8%, or maybe they claimed that pi was less than or equal to 8%. If they did, these would be HOs. But if they had claimed pi was greater than 8%, then I would have written that as HA. So again, I put this in our summary document, but I just wanted to point it out now. I don't want to get too wrapped up in this. Step number 3. This is where we set our significance level. In this case, they say test the claim at alpha equals 0.05. Remember, this is just the opposite of confidence. So think of this as being similar to a 95% confidence interval. Generally, we'll use numbers like 1% or 5% or maybe 10%, you know, again, corresponding with 90% confidence, 95% confidence, or 99% confidence. This is called the significance. Basically, what this means is we will accept that there's a 5% chance that we are going to reject the null hypothesis, even though it's true. That we'll get some weird data that would cause us to reject HO, even though it's actually true. Just like we said in confidence intervals, that there's a certain percentage of the time where we will make a mistake and our interval won't contain the population parameter just due to dumb luck in our sampling procedure. Same thing here. We're accepting that there's a 5% chance that we're going to reject the null hypothesis, even though it's true. You might say, why wouldn't we make it lower? Why wouldn't we make that 1% or 0.01% or 0.001%? Well, the consequence of making this too small would mean we'd raise the probability of making a different error. And that error would be failing to reject the null hypothesis when it's wrong. So there are two things that can go wrong here. We can reject the null hypothesis when it's true, or we could fail to reject it when it's false. And the two are very strongly linked. If I reduce the probability of one, I raise the probability of the other. And that's why we tend to set this early on in the process, and we tend to not make it super small because we know the consequences. It raises the probability of the other one. Step 4. This is where we check to make sure that we can actually do the problem, that we have enough data. For checking proportions, we check that n times pi is greater than or equal to 5. In this case, we sampled 1,600 windows. And we're assuming the null hypothesis is correct. So we get to use that value in our calculation. $128 is greater than or equal to the magic number 5, so that's okay. And then we have to check n times 1 minus pi. So that'll be 1,600 times 92%. and we get 1472, which is also greater than or equal to 5. It checks out. This tells us that we can use the Z distribution. This is maybe the most important step in the whole process, even though it's a step students never want to do, or people in general don't want to do. A lot of stats software will run a hypothesis test for you, and people will just blindly run them without ever checking to see if they were allowed to run them in the first place. If we had sampled much fewer windows, say we only sampled 5 windows or something, well then 8% of 5 wouldn't be greater than or equal to 5, and we shouldn't do it. So this is an important step, is checking the assumptions. If you're trying to annotate what the steps are. Step 1 is write down the claim. Step 2 is set up your alternate and null hypotheses. Step 3 is set the significance level. It's generally given. Step 4 is check your assumptions. Step 5, we finally get to start doing some real math. We calculate the test statistic. When we're testing pi, the test statistic was given on the previous page. It's p minus pi all over pi times 1 minus pi over n, a bit of square root. So now we just plug in our values to calculate this value. Basically, we're trying to see if our sample results are unusual relative to the null hypothesis. So what is P? Well, that's our sample data, 160 out of 1600. 10%. And pi, we get to use the 8% again, because we're assuming that that statement is true. It's our working hypothesis. Pi is 8%. We do a little calculation here. I get 2.95. Remember back a couple steps ago where I said that we had to have an equal sign for the null hypothesis. Well, these are the reasons why. We're directly substituting in 8% for pi in a few places already. So it had to equal. We had to assume that it actually equaled it. So that's why the null hypothesis will always have to have an equal sign, because we will do these substitutions in our calculations. Now, we've been doing this course for a long time now. You probably recognize that this is a strange z-score, right? Or it's at least borderline strange. When you have a normal distribution, if you're more than 2 standard deviations away from the mean, you tend to be unusual. So something unusual has indeed happened. 160 out of 1600 is unusual if we are assuming that the actual percentage that are defective is 8%. So you can see how we're setting this up. We're going to say, I don't believe this null hypothesis because my sample results seem weird if that's true. Now I'm trying to say this in layman's terms here. We want to formalize this. So we'll construct critical values to compare this number to, rather than just sort of eyeballing it and going, oh yeah, 2.95, that seems kind of high. So that's what step 6 will be about. There are actually 2 methods for step 6. There's the classic method and the p-value method. Maybe I'll break it up and I'll do them both. The classic method involves critical values. Just like we had from confidence intervals. So the classic method, when you're first learning this, is trying to show us the link between confidence intervals and hypothesis testing. Now, in real life, most statistical journals, in fact, every time I'm reading anything, I see people using the p-value method. So the p-value method tends to be more respected in academic, journals and such, whereas the classic method is the way that you first learn it, just so you can see how things are tied together, so that the course doesn't seem disjoint. So let's try the classic method first. I said we're going to calculate some critical values. This is a two-tailed test. We're going to find critical values in the upper tail and the lower tail. And then we're going to compare our test statistic to those critical values. In this case, because it is two-tailed, we'll have two critical values, just like we always did in confidence intervals. There is something called a one-tailed test, which I'll show you next. This one is two-tailed. Let me go back and I'll tell you why. Our null hypothesis was that pi is 8%. What would make us disagree with that? Well, we would disagree with that certainly if we got numbers way bigger than 8%. So anything strangely high should be rejected. But we would also reject this if we got a number that was strangely low. Like 1% might be very strange relative to 8%. So there are two conditions that would make us reject this null hypothesis in favor of the alternate hypothesis. And because of that, we'll have a cutoff on each end. You probably already know where I'm going here. In this case, we already set alpha. So we know that we're going to use 0.05. So the area in the upper tail and the area in the lower tail have to equal a total of 0.05. Each tail it's symmetric, so alpha over 2 is the area there, so 0.025 on each side. You can look up 0.025 in your negative z table, and you know that you're going to find negative 1.96. And if you looked up 0.975 in your z table, you know you'd get 1.96 on the other side. 0.95 is here in the middle. Now we're going to compare our 2.95 to these numbers. And when we do that, we will see that 2.95 is unusual. It's in this upper tail. So if we're assuming that the null hypothesis is correct, then this value is unusual. If we're going to do that, then we can start to make a decision. That's what step 7 will be. It's our decision. In this case, because 2.95 is unusual, it's in the rejection region. That's what anything bigger than 1.96 or smaller than negative 1.96 is the rejection region. 2.95 is in the rejection region. So our decision will be, whoa, bear with me, lost my page here, right at the punchline. Okay, our decision will be, because this value is in the rejection region or is unusual, we will reject the null hypothesis. Don't mention the claim yet. All we're doing in the step 7 is we're evaluating our original null hypothesis. Do we reject this hypothesis or do we fail to reject it? Don't say accept it. I know it's a subtle difference, but it's related to, are you guilty or are you innocent? Or are you guilty or not guilty? We use that same sort of wishy-washy naming here. We will reject the null hypothesis or we will fail to reject the null hypothesis. Mostly we want to keep it somewhat wishy-washy because there's a probability that we made a mistake. In fact, we know what the probability is. There's a 5% chance that this conclusion is wrong, that we've rejected the null hypothesis when we shouldn't have. And that will be reflected in our final step here. Step 8 is your conclusion. Our conclusion is there is sufficient sample evidence at a significance level of 0.05 anyway this is where we're going to start talking about the claim, to reject the claim that 8% of delivered windows are damaged. So in step 8, we finally put things back together. We know we've rejected the null hypothesis in step 7. Let's go back to the beginning and see what that means. If we've rejected the null hypothesis, we have rejected the claim because the claim was the null hypothesis. And we get to word this fairly strongly. There's sufficient evidence to reject the claim. And the reason this is worded fairly strongly is we know the probability of our error. There's a 5% chance that we made a mistake. We can quantify the probability of our error. And because we can measure the probability of our error, we can word our conclusion fairly strongly. You'll see examples as we go along where we sometimes can't word our conclusions as strongly because we don't know the probability of our mistake. If you have a 5% chance of rejecting the null hypothesis, even though it's true, it's impossible to know what the probability of not rejecting it when it's false unless you know what the actual answer is. So it's one of those situations where you can't say what that second probability is. We call these type 1 errors and type 2 errors. We know the probability of the type 1 error, that's alpha, but we don't know the probability of the type 2 error. We just know that it's somehow linked to the type 1 error. This is our hypothesis test. We set up a claim. We write our null and alternative hypotheses. The claim sometimes is the null hypothesis, and it sometimes is the alternative. In this case, it was the null hypothesis because the claim had some form of equality. Then we set up our significance level. Usually it's given. Usually it's 5% or 1%, sometimes 10. Then we check to make sure that we can even do the problem. Then we calculate a test statistic. Then we want to evaluate our test statistic. One way is to compare it to critical values. If your test statistic falls in the rejection region, you reject the null hypothesis. If this number had fallen between negative 1.96 and positive 1.96, then it's not in the rejection region, and we would have failed to reject the null hypothesis. But in this case, it was in the rejection region. It was in the upper tail, which caused us to reject the null hypothesis. The null hypothesis was the claim, so we rejected the claim. We basically said, we don't think that 8% of these are broken. We don't necessarily conclude we think it's higher, but I mean, that is where our evidence is pointing. Now, there's another way to do step 6. All the other steps remain the same, but I left myself a little bit of space to do step 6 using another method, the more preferred method in the literature. It's the p-value method. So let's do that as long as we're doing this example. The p-value method is simply calculating, the p stands for probability. So it's the probability of observing results as extreme or more extreme than we have, assuming the null hypothesis is correct. Maybe I should write that. The p-value is the probability of observing sample results as extreme or more extreme under the assumption that the null hypothesis H sub 0 is true. Throughout this whole procedure, we assumed the null hypothesis was true right up until step 7. We finally had enough information to say we're not going to work with that anymore. We used the critical values in our first attempt at this. Now we're going to calculate the probability of getting results like we did, or more extreme than we did, assuming the null hypothesis is correct. And when we're doing this method, we also have to check to see if it's one-tailed or two-tailed. In this case, it's still a two-tailed test. Let's calculate the p-value. We observed a value of 160 out of 1600. We're going to see what is the probability of getting a result like that if it is true that the actual probability is 8%. You know, we think 10% are broken, but we're assuming that 8% are usually broken. Is our observed result weird relative to what it's claimed? Or in this case, what we're assuming it to be. So let's find the probability of getting a z-score of 2.95 or higher. So 2.95 would land here on our z distribution. Remember, 0 is in the middle. So, and that's what this is. The probability of observing results as extreme or more extreme. Well, here's our value. What would be more extreme than that? Well, that would be going to the right. You know, this small area to the right. Now, because it's a two-tailed test, it could just as easily have been the case that we got something that was a little bit bigger than 8%. Or smaller than 8%, I should say. Maybe if we'd done this again, we would have had 6% broken. So under the two-tailed version, we'll have to figure out the probability of being smaller than negative 2.95 as well. When it's a two-tailed test, you'll have these two regions. The p-value is the sum of those two regions. But because it's symmetric, we can just double it, right? We want our p-value is just 2 times the probability that we have a z-score greater than 2.95, right? Find this area and it equals that area. Or maybe you prefer to use your negative z table. It's 2 times the probability of being under negative 2.95. Either way. If you had Excel, 2 times norm.s.dist of negative 2.95. That would give us the area under the curve down here. And then we double it. From our z table, we can just jump to those. We have a negative z table. We're looking for negative 2.95. See, this table gets a workout. Let's erase this other stuff. 2.9. And what column are we in? So our probability of being in that lower tail is 0.0016. Maybe I'll just write 2 times 0.0016. So we get 0.0032 for our p-value. Each side here has an area of 0.0016. So the total p-value is 0.0032. That's a pretty low probability, right? The probability of getting a z-score like this is quite low when we assume that pi is actually 8%. So either we have strange data or pi isn't 8%. So rather than just saying this is a low number, we need something to compare it to. And this is another place where we use alpha. We used alpha in our classic method to determine what the cutoffs were, and we're going to use alpha again in our p-value method. All you have to do is compare your p-value to alpha. If p-value is less than alpha, reject the null hypothesis. Otherwise, fail to reject null hypothesis. If p-value is greater than or equal to alpha, then our conclusion is fail to reject HO. I can't. In this case, 0.0032 is smaller than what alpha was. So we're into step 7, which is reject the null hypothesis. And then we're on to our conclusion saying we reject the claim in this case because the claim was the null hypothesis. The second method is what's preferred, but it might seem a little, more foreign than the classic method if you're already used to doing confidence intervals. But we're pretty good with our probabilities, so I think you'll be okay with this p-value method. I may ask both. So on a test, I might say, conduct the following hypothesis test using the classic method. Or I might say, conduct the following test using the p-value method. So you will need to know both. And that's it. That's a hypothesis test. It took us a while to do just one of these. Hopefully they'll get faster because I won't be blabbing as much as we go through them. Let's try the same one again, or something very similar to help keep it nice and familiar. Again, we have 1,600 windows, and again, 160 were damaged. But now the claim is going to be different. The company is now claiming that it's actually under 8%. They claim that less than 8% are broken. And that's what step 1 is. Write down the claim. Step 2. Write down your null and alternative hypothesis. Basically, figure out where to put step 1. Step 1 does not have an equal sign in it, so this is not going to be my null hypothesis this time. It will be the alternative hypothesis. My null hypothesis will then be the opposite. Basically, the closest call between these two cases is when pi equals 8%. So we're essentially going to assume that it's 8%. And if it works for the 8% case, well, then it will work for anything bigger than the 8% case. So you'll sometimes see people write it that way. I'm not sure which I prefer. I think I used to prefer this way, but I think students found it confusing when the null and alternative weren't opposites. So I think it's maybe better to write it like this, at least when you're first learning it. Step 3 is set your significance level. This is your probability of a type 1 error, and it's given. It's the same as it was before. There's a 5% chance we're going to reject the null hypothesis, even though it's true. But in this case, the null hypothesis isn't the claim. If we reject the null hypothesis, that's actually, good in that it would then support the claim. Step 4, check your conditions. Make sure that n pi is greater than or equal to 5. And we already did this. I forget the number already, but I know it was greater than or equal to 5. And I know that n 1 minus pi is also greater than or equal to 5, and that lets me go ahead and use a z distribution. Step 5 is calculate your test statistic. You have a formula sheet for this. Back in my day, we had to memorize these things. And we'd already plugged in the numbers. It was, again, 2.95. So really, not much has changed with this example, except these, our arrows here are inequality signs. Step 6. We could do it 2 ways. Let's do it both again. You would never do it both in real life, but just while we're learning it. If we're going to do this the traditional method, we're going to find a critical value or critical values. In this case, this is not a two-tailed test. This is a one-tailed test. And when it's a one-tailed test, it's either a left-tailed test or a right-tailed test. How do you know? Let's go back to the original setup. Look at the null hypothesis here. Pi greater than or equal to 8%. What's weird in that case? If you got a percentage that was, say you got 90% of the windows are broken, would you reject this? No, you're fine with it. It's bigger than 8%. Greater than or equal to it. But if you ended up with only 1% of your windows broken, well, that would be unusual under this assumption that it's greater than or equal to 8%. So we're only really worried about the case where we have smaller than. So on the left side, this is a left-tailed test. If you need a way to remember it, look at the alternate hypothesis. HA points the way. The arrow, the inequality, is pointing to the left. Basically, what would make you support HA? Things on the left. So when we do our critical value, we'll only have one. This is new. In our confidence intervals, we always had an upper and lower bound. Hypothesis test can be one-tailed, where we only have to worry about the one side. So instead of having a Z written with alpha over 2, I'm going to write it just with a subscript alpha. All of my error will be on this one side. In this case, on the left side, because that's a left-tailed test. All our area is on this end. We could look up 5% in our negative Z table, and we'll get our answer. If you're an Excel person, I guess you'd do norm.s.inv. Remember, S means standard normal, so Z score. I almost wish it were norm.z.inv. And then you just put your percentage. If you're a table person, you go back to your Z table and you start searching around inside the table for 5%. Basically, you're reading the table backwards. If you look in your table here, I think I see 5% somewhere around here. It's actually exactly halfway between these two. So we can say it's negative 1.64 or negative 1.65. And because it's halfway between, we can say 1.645. Get one more decimal place of precision. Anything to the left of negative 1.645 is weird. Our value is not there. It's way up here. It's not in the rejection region. So we're not, you know what our conclusion is going to be here. We're going to fail to reject the null hypothesis, even though, we kind of got in the habit of saying, well, 2.95, that's a weird Z score. It's weirdly high, but we don't care about weirdly high Z scores in this left-tailed test. We only care about weirdly low ones. So this is not that unusual under this assumption. Step 7 will be fail to reject the null hypothesis. This is not unusual based on the data that we observed. Which makes sense. Let a little common sense seep in here. 10% of your windows are broken. And somebody says, I think it's more than 8%. Yeah, you're probably going to agree with them in that situation. So rather than agreeing, though, I'm just going to say, I'm not going to disagree. I fail to reject the null hypothesis. And then in step 8, I can write my conclusion referencing the claim. If I don't reject the null hypothesis, then I'm not supporting the claim. Remember, the claim in this one is HA. So if I do not reject HO, I'm not supporting the claim. And now we'll write that up. There is insufficient sample evidence, at least at alpha equals 0.05, to support the claim that less than 8% of the windows are delivered damaged. Notice how the wording of that is fairly weak. Basically, it's saying we can't, instead of saying they're wrong, we say we can't support that they're right. And the reason for that is that we don't know the probability of our error. When we reject the null hypothesis, we know the probability of our error. But when we fail to reject the null hypothesis, we don't. That's the type 2 error situation, which we can't know the probability of without knowing the actual answer. And therefore, we have to be careful in our final wording. We have to just say, keep these wordings very weak when we have failed to reject. This is a complicated thing, the wording of the final answer. I thought I would help you out, and I made a little chart to help with the wording of the conclusion. Basically, in the example that we just did, our claim was the alternate hypothesis because it didn't have an equal sign in it. And then our decision was fail to reject HO, and then we word our answer accordingly. You'll notice that in the fail to reject cases, we have weaker wording than the reject the null hypothesis cases. So I'm very picky about this wording. So make sure that because you have this little chart available to you, make sure you check it before you write your conclusion. Because if you are off by a little bit, like if you forget the in part of insufficient, like, in one version there is sufficient evidence, in another version there is insufficient evidence. In some of them you say to support the claim, in some of them you say to reject the claim. If you get that twisted around, you can actually end up with the exact opposite meaning of what you're intending. So make sure you get these right. Follow the chart and everything will be fine. We finished this example, and common sense did sort of prevail. If somebody says, I think it's the 8% of less than 8% of something is broken, and you do a little test and your percentage is quite a bit higher than that, well, then they're probably wrong. So this thing did kind of agree with what our common sense would have told us. Sometimes you get so wrapped up in, step 1, step 2, step 3 that you sort of forget what you're doing. So don't completely lose track of that. I want to do step 6 again as a p-value. The p-value method we said is just calculating probability of getting a result as extreme or more extreme than you observed. Well, it really depends on what kind of test it is. In this case, left-tailed. Remember, HA points the way. Our value that we observed for Z was 2.95. Now, what is more extreme than 2.95 when you're headed to the left? That's anything smaller than 2.95. That's this big area. So we're going to end up with a large probability. When I wrote the definition for p-value, it was kind of vague, more extreme or less more extreme than what you've observed. And I use the word extreme rather than bigger or smaller because it depends on which direction you're going. If you're headed to the left, you shade to the left. If you're headed to the right, you shade to the right. And if it's two-tailed, you shade a bit up in the upper tail and a bit in the lower tail. So in this case, my p-value is this shaded region. It's the area to the left of the critical value. I'm sorry. Its p-value is the area to the left of the test statistic, the 2.95. So we want the probability of a z-score being less than or equal to 2.95. That's our p-value. You can just look up 2.95 in your Z table. Or if you had Excel available to you, you just say norm.s.dist 2.95, and yes, it is cumulative. Let's go look up 2.95 in our Z table. I have my negative Z table open here. Let me go to my positive one. Not that I couldn't have figured it out from the negative. We're looking for 2.95 now. So 2.9 is in this row. And we're in column 5. So our area is 0.9984. That's a big p-value. So our step 7 would be, since the p-value is greater than alpha, fail to reject the null hypothesis. Your p-value method should always give you the same result as the traditional method. It shouldn't matter which one you use. It's just that the p-value method is more accepted in the scholarly literature. The reason for that is in the literature, they don't usually write out all these steps. Basically, the literature will be very brief. It'll just have one little paragraph that says, we conducted a test of 1,600 windows. We were testing a null hypothesis that the proportion was greater than or equal to 8%. The p-value for the test was 0.9984. And then it's up to the reader to make their own decision. The reader would know, well, that's a big p-value, so I know I would fail to reject. And by big, I mean it's nowhere near the typical choices of 5% or 1%, or maybe even 10%. So it allows the reader to basically choose their significance level, and then they know there's nothing fishy going on like when you choose your 5%, you might adjust this 5% so that you get a different critical value, so that maybe you end up with a different conclusion. It really stinks when you have a hypothesis test where the critical value is close to your test statistic, because that means you can change the answer based on what the value is for alpha. Typically, those sorts of tests would never get published anywhere. If your p-value is close to 5%, the conclusion is you don't have enough data to make a good conclusion. Go back to the drawing board, do your experiment again, do a larger sample size, and hope that the next time you end up with a p-value that's further away from 5%. This is often sort of a deceptive statistical technique where if I'm a professor at a university and I'm doing research for 5 years on some topic, and the university really needs me to publish something in order to let me keep my job, well, I might be tempted to manipulate this p-value to be something that is far away from alpha, so that I can actually publish my paper, so that I don't lose my job. So there's been a lot of discussion about this whole p-value. I just told you it's the preferred method, but it also has the potential to be abused because, well, people's jobs are sometimes on the line. So we'll have to be always suspicious of p-values as much as everything else in statistics, even though it is the accepted way of doing things, assuming that people understand what it means. When the p-value is very close to 5%, you can't really make much of a decision. But when the p-value ends up being something really tiny, 0.000000001, that's great, because then you're nowhere near alpha, and you can make your conclusion, more reliably. It's more trusted. So it's those gray area cases that are tricky. Yeah, that's hypothesis testing for proportions. We're going to repeat this now, doing hypothesis testing for the mean. Why not? We're going to do a bunch of different hypothesis tests now. We'll test a single mean. We'll do comparison of multiple means, or two means. Then we can do multiple means. We can compare two standard deviations. We can compare, there are many, many hypothesis tests out there. We are going to do enough of them that basically whenever we run into a new situation, it would be easy to learn a new method, because we've already done a bunch of the different tests. So that's it for this video. We'll take that up with the next one. I will see you all next time. Have a good one.